When you first look at this image, it may not look like much, just a couple of shapes. But these shapes represent all of the things necessary to begin describing the basics of path tracing. It's actually a 2D representation of a 3D scene. It might be obvious to you what's what, but let's begin by labeling what we have. In every scene we have lights, a camera, and nope, not that. There we go. Objects. As you can see here, the camera is represented by the triangle, the light by the yellow circle, and the objects by the red circle and gray rectangle. These are all the components we need to begin explaining ray tracing, and by extension, path tracing. To start, there are a couple of concepts you need to be familiar with, the most important of which is the ray. As you may remember from some math class long ago, a ray is a point in space and a line that continues out from that point indefinitely. A ray in path tracing is no different, except that it can be stopped by an intersection with another object. The other concept important to path tracing is to think of your render not as an image, but as a grid, more specifically a grid of pixels. With those concepts under your belt, you're ready to start learning about ray tracing. Back in the original diagram, let's fire a ray into the scene and explain what happens to it along the way. First, the camera acts as an origin point for all of the rays we'll fire into our scene. And it fires them through an image plane, which becomes the pixel grid we talked about earlier. Now you may be saying, I'm fairly certain that my eyes aren't firing light out into the world in real life, and this would be accurate. In the real world, rays are fired from light sources. However, the total number of photons fired from a lamp in the real world is much greater than the number that actually hit your eye. In order to save a crazy amount of time when rendering, we just reverse the process and trace them backwards. This ensures we're only calculating the paths of important rays. Under the hood, a path tracer has a very large value that operates as a maximum distance for a ray to travel. If it hasn't hit anything by the time it reaches this distance, it will either return a flat color, usually black, or possibly the background color, or even no value at all if you're rendering with alpha values. But what happens when a ray hits an object? For the sake of this exercise, we'll say that the ground is diffuse and the red circle is perfectly reflective. Let's fire a ray at the ground. Remember, the ground is a diffuse surface. So we've hit this point. The first thing that's going to happen now is a shadow ray is fired at the direction of one of the lights in the scene. If anything is hit before it reaches that light, we know that this point is in shadow of another object. In this case, we know that the point is inside the shadow of the sphere. So, this information is stored, and the value of that pixel on the grid is given a value of 0, or black. If we're using direct lighting, meaning no additional bounces, then we're done with this sample for this pixel. And that's really all there is to ray tracing. There's a lot of additional functions in an advanced engine like Cycles, but this is the calculation at the core of all ray and path tracers. So, how is a path tracer different than a ray tracer? Well, there's not a set definition. A path tracer is generally regarded as a system that takes the basic ray tracing result and repeats it X number of times per ray. Meaning we could take the result of the ray we just traced and go one step further, and another, and so on and so forth, until we've either hit a user-defined bounce limit, or the ray has so little energy left that it's not worth keeping track of anymore. In reality, bounces should be infinite, but there's no such thing as infinity in computers, and even if there were, we wouldn't want to wait for it to compute. So we take these shortcuts.